EtherCAT as a master machine control tool. My name is Liz Wright, and I'm the Marketing Manager for the Motion Control Association. This webinar will be recorded, and a link will be sent to you within the next 24 hours. If you have any questions, please submit them in the questions panel of your webinar screen, and we will answer them at the end during the Q&A section. Any additional questions will be answered via email after the webinar has concluded. I'd now like to introduce you to our presenter for today's webinar, Matt Clint from Galil Motion Control. Matt Clint joined Galil in 2013 as an applications engineer. Before coming to Galil, he worked as a development engineer in the physics department at UC Davis, where he was involved in developing hardware and software solutions for experiments in condensed matter and astrophysics. Matt has brought his expertise to Galil and has worked with numerous research institutions on motion control and data collection projects. At Galil, he has worked closely with other applications engineers and R&D on development of Galil's EtherCAT-compatible controllers. Matt holds a BS in physics from the University of California at Davis. I'd also like to thank our sponsors of today's webinar, Galil Motion Control. With over 750,000 controllers sold, Galil is a leading manufacturer of motion controllers and PLCs. Since the introduction of the first microprocessor-based motion controller in 1983, Galil has remained one of the industry's leading innovators. By offering its customers powerful, cost-effective, and easy-to-use motion controllers and PLCs, Galil is committed to be your primary source for any motion control and I/O application. Galil's unparalleled array of motion controllers and PLCs are backed by superior technical support and can accommodate the most demanding applications with absolute precision. I also would like to thank our other sponsor, Electromate. Electromate is the exclusive Canadian distributor for Galil Motion Control and specializes in high-performance robotic and mechatronic systems, including servo and stepper motion solutions, positioning actuators, and robots. Electromate's extensive product selection is backed up by its just-in-time delivery and stocked inventory. Electromate also offers engineering assistance and technical support by their dedicated customer service team. Now I'd like to hand it over to Matt to begin today's presentation.
Good morning. Thank you for joining us for EtherCAT as a master machine control tool presentation. My name is Matt, and I'll be presenting today. This presentation will lay out in broad strokes the EtherCAT communication protocol and the types of applications that can benefit most from its use. In addition, I'll introduce the Galil Motion Control DMC 50000 EtherCAT Master and review its capabilities. Afterward, Galil's Vice President of Engineering, Kaushal Shah, will join us to answer additional questions. So let's go through the agenda first. First of all, I'd like to tell you a bit about Galil Motion Control, followed by an introduction and overview of EtherCAT communication, and then go over the DMC 50000 EtherCAT Master, summarize, and then we'll start the Q&A. So with that being said, a little bit about Galil. It was founded in 1983 by Dr. Jacob Tal and Wayne Barron, and was the first company to introduce microprocessor-based digital motion controllers. Galil also pioneered the technology for controlling servo motors with only the position feedback, removing the need for a tachometer. Today, Galil offers its fifth generation of motion controllers with a 32-bit RISC-based microprocessor combined with Galil's custom ASIC to solve the most demanding motion control applications. As a pioneer in the industry, Galil introduced the first Ethernet-based controllers in 1999 and have shipped over 100,000 motion controllers in the industry that communicates via TCP/IP connectivity. Galil has been developing and selling motion and I/O controllers worldwide for over 30 years and has built an established reputation as a leader in the motion control and automation industries. Our primary goal is to provide customers with the best products, services, and value while providing solutions to customers' needs. Towards that end, we work hard to ensure that our controllers are feature-rich enough to cover most applications requirements. To a large extent, most customers find that our standard products are more than capable of meeting their applications requirements. That being said, we pride ourselves on our ability to work with customers on custom hardware and firmware that will meet their specific needs. Our commitment to customer support and education is the driving force behind our applications engineering department. With more than 100 years of collective experience, the application engineers offer expertise in various fields, including electrical, mechanical, mechatronics, computer science, and applied physics. As a collective group, our focus is to work with our OEM customers to offer the most cost-effective solution to their motion control needs. If you cannot find a motion controller or PLC to meet your requirements, then our applications engineers will work with you to define and develop a custom product to meet your specifications. Let's move on to communication protocols. Let's start the presentation here. So the benefit of communication protocols in general is that standardization allows cross-platform integration, meaning that any vendor that wishes to develop a product has a set standard of communication protocols that it can work with. Mainly keeping it simple. Running a serial or Cat5 cable between components is much easier or cheaper than wiring motor power leads, encoders, etc. Modular design. Each component is self-contained, yet works in concert with the rest of the components in the network using an agreed-upon communication scheme. The modularization means it's easy to replace, easy to expand. Since they're self-contained, one or two cables can be swapped to connect hardware. Wide market. Open protocols allow any vendor to develop compatible hardware, giving the customer a broad range of options for their application. Specific to today's presentation, we'll discuss the EtherCAT communication protocol. EtherCAT stands for Ethernet for Control Automation Technology. It was invented by Beckhoff Automation in 2003. It's an Ethernet-based field bus optimized for industrial automation control, essentially taking Ethernet communication and stripping it down to the bare essentials that's needed for motion control applications. Based on CANOpen, the device profile for embedded systems used in automation. And the standards are defined and maintained by the EtherCAT Technology Group, or ECTG. EtherCAT and Ethernet. EtherCAT is based on the physical layer of Ethernet, but there are fundamental differences that distinguish them. Ethernet is designed to move large amounts of data through many nodes. It's able to route data to and from billions of separate addresses, allowing communication across vast networks like the Internet. Large overhead. There is a large overhead associated with Ethernet communication in that it must contain a source address, a destination address, a type, and that's a lot of processing on each side of the transaction. And software handles the extraction and processing of data. EtherCAT, on the other hand, uses standard Ethernet hardware, Cat5 cabling and network interface cards. It streamlines Ethernet communication at the hardware level. Data processing on slave devices is handled on the fly via FPGA or ASIC, minimizing latency. This is in contrast, as mentioned, to Ethernet, in which software handles the processing. The flip side of that is that initial setup and configuration of the EtherCAT network is required. So let's go over Ethernet frames first as a baseline. An Ethernet frame being sent down the Cat5 cable from a host to another PC consists of an Ethernet header. This is built up of the destination address, so the address of the device that's sending the packet, and the source address, the address to which that packet is being sent. The ether type is defined as, it specifies the type of communication being implemented. The hex 0800 specifies IPv4, which is the predominant protocol for internet communications. Ethernet data then follows. The payload is the particular data that's being transmitted and can consist of up to 46 to 1500 bytes per packet. And the CRC checksum at the end of the frame, which is essentially a checksum to check the validity of the data upon receipt. As you can see in the figure below, the majority of the Ethernet packet is going to be the data. EtherCAT frame is very similar to an Ethernet frame. There's a few subtle differences that accentuate the speed of the protocol. The Ethernet header, ether type 08A4, specifies EtherCAT specifically. Or the Ethernet header. EtherCAT header includes the data length to tell the slave down the line how much data is going to follow in the packet. 1 bit is reserved by the EtherCAT organization for future use. And then there's the protocol type. 4 bits and indicates the hex 1 indicates CAN over Ethernet as opposed to the other, or over EtherCAT, as opposed to the other EtherCAT designations. EtherCAT data, similar to Ethernet, can consist of up to 46 to almost 1,500 bytes, but the EtherCAT header does take a small amount out of that data. But as we'll see later, EtherCAT data transmission is very efficient and rarely needs that many bytes for transmission. The working counter is a part of the EtherCAT frame. When the Ethernet network or EtherCAT network is brought up, each drive that is active on the network will increment this number by 1. So essentially, it's a head count of how many active drives are on the network. If the master detects that this number changes during operation, an error flag will be set and handled as per the master's routines. So it is a safety implementation built in the background to handle, to make the network more robust. Each drive on the network has a unique address, typically set with hardware switches, rotary switches, or dip switches set on the actual drive. The master-slave configuration with the EtherCAT master sending and requesting data from the slave. Data that is not addressed to a particular slave are immediately forwarded along to the network. This is as opposed to Ethernet traffic, at which at each router, at each node, the packet is taken apart, the source and destination address are looked at, and then it is routed to the next node. EtherCAT benefits from a minimal processing time. It can provide cycle rates or cycle update rates of up to 32 kilohertz. Network layout size is limited only by the allowable lengths of Cat5 Ethernet cable, and according to Ethernet communication standards, this can be up to 100 meters in some cases. Another key benefit of EtherCAT communication is increased noise immunity due to reliance on Ethernet physical components. Ethernet is a differential standard, or communication standard, which is much more noise immune than twisted pair shielded cables over 4-encoder or motor command lines. EtherCAT communication analogy. The most often used analogy is that of a train. Essentially, the EtherCAT packet heading down the Cat5 cable from the master to the slaves is a train, subway. The EtherCAT line picks up and drops off data, which are analogous to passengers at each station. This analogy does break down when you consider that it requires the train does not stop. An Ethernet packet is not halted at each drive. It is on-the-fly processing to increase speed and efficiency of communication. In my opinion, a better analogy is that of a cubicle farm. I think most engineers can relate to that. Each cubicle represents an EtherCAT slave. Each engineer is told where to sit by an SDO, we'll get to that later, and a hex address. Essentially, the hex address, or the physical address assigned by hardware switches, is where HR tells you to sit, essentially. The boss, appropriately, is the EtherCAT master, sending instructions, PDOs, again we'll cover that in a bit, out to the engineers each morning and picking up their work at quitting time, or the end of the day. And this happens at a deterministic rate. So each morning, on the second, each afternoon, at at quitting time. So every morning, right, your boss comes through without talking to the boss. Boss comes through, puts your assigned tasks into your inbox. You grab it, and without talking to the boss, start executing your tasks dutifully. So starting to stretch the analogy a bit, the PDO, which is sent down to you, is a work order for the day. An SDO is a priority list you receive before instructions that tell you the order in which to perform the tasks. So the bottom line is that EtherCAT, although not a very effective strategy for the office, which does not encourage any kind of communication, is very efficient for deterministic servo control. EtherCAT network operation modes include the following. In profile mode, motion profiling is largely left to the slave. Parameters are set on the drive, like acceleration, deceleration, speed, etc. The master simply sends target positions, either target positions, speeds, or torque, to the slave, which then does its own math and profiling to make sure it reaches the target in the allotted amount of time. Cyclic modes of motion are more analogous to motion control that would be on a single controller. Cyclic mode, master sends commands to the slave at a predetermined regular rate, or cycle time, providing targets with each iteration, whether that be position, velocity, or torque. In position mode, the slave has PID and motion parameters set on each drive. So motion profiling is handled on each drive. In torque mode, PID parameters are set on the master, which then simply sends calculated torque commands based on the error measured between the reference position and encoder position on the drive. Cyclic velocity mode is very similar to position mode, except that instead of sending position profiles, you are sending velocity profiles. In the previous, as relates to the previous analogy, profile mode leaves tasks up to the slave complete. As long as the slave completes its task on time, the EtherCAT master is happy. Cyclic mode is micromanaging to the nth degree, dropping in on a regular interval on the EtherCAT network up to 32,000 times a second to tell you what to do and how to do it. Again, as an employee, not a company you would want to work for, but very effective communication for closing the servo loop. So let's move on to the properties of both the EtherCAT master and the EtherCAT slave. EtherCAT master can be any software or hardware that's configured to assemble, send, and receive EtherCAT datagrams. This is one of the strong points of the EtherCAT protocol. It is an open protocol. Anyone is open to implement it. Requires only standard Ethernet physical layer components for communication. The only specialized hardware is purchased inside the drive. In terms of communication with the drives, all that's required is a Cat5 cable, as well as a standard network interface card. Facilitates coordination between EtherCAT slaves, writing and receiving data from each slave in EtherCAT frame. Hence, the master-slave layout implies that there's one controller, one program that's controlling the network. As pertains to motion control applications, the relevant data sent to the drives are profiling data, so target position, velocity, or torque, input-output settings, and the data requested are position and input status. In order for the master to calculate where the drive should be at the next cycle update time, it requires knowing where the motor is currently to calculate the error for the PID filtering to act on, as well as input status, which can indicate the status of limit switches or other digital or analog I/O. The EtherCAT slave is really is really where the EtherCAT communication protocol comes into play in the way that it reads and processes profiling data, and that it writes position, input, and drive status for return to the master, can be configured in multiple modes and operation. All slaves, as according to the EtherCAT standard, all slaves contain specific spaces in memory where data can be written. These spaces are called objects. The entire memory space is called the object dictionary. Each object has its own address specified as an index or subindex. For example, the operation mode data from the master is written to the hex 6060 object in the slaves dictionary. Operation mode data corresponds to whether you're in position mode, velocity mode, cyclic torque mode, cyclic position mode. While position commands in the cyclic position mode are written to the hex 607A object. How is this data sent? Data is sent based on the CANOpen SDO and PDO packet structure. Data is moved along an EtherCAT network using two protocols, SDOs and PDOs. An SDO is known as a service data object. SDOs can be sent at any time, whether the network is operating, running a servo system, or before or after during real-time operation. However, they do require additional communication overhead in that they contain specific addresses as well as checksums and as well as acknowledgments back to the master. As a result, SDO usage is typically only used for network setup. PDOs, these are the workhorses of the EtherCAT network. PDOs contain the raw operational data with minimal overhead, and thus are used for real-time processes like motion and I/O control. PDOs can only be used once they're mapped using SDOs. We'll get to mapping a little bit later. Mapping sets up each byte, which byte in each PDO goes to which memory address on the slave. And this is really the secret sauce of EtherCAT. Instead of the EtherCAT frame coming in, software disassembling the packet and assigning data to each address, the position in the PDO is what of the data in the PDO after SDO setup is what defines where that data goes in terms of which slave, as well as what data, whether it be positioning data, I/O status, drive status. This is just a general summary. SDO contains a transfer confirmation, which increases the overhead. The benefit is that the master is assured that the data was received and written to the drive. PDO contains no transfer confirmation. It's essentially sent out onto the network. And it's assumed that that data is received and read. SDOs are a client-server model, whereas there's one server logs into the clients and sends data to them. PDO is a peer-to-peer model, where any slave at any time may initialize communication or send data down the line. However, in most servo applications, communication is coordinated by the master. SDOs are typically used only for device configuration and PDO mapping. PDOs are used high priority transfer, small amounts of data. So the PDO packet size is kept to a minimum, typically 8 bytes or less. SDOs can be sent at any time. So whether in initialization mode, configuration mode, or even during real-time operation, SDOs can be sent. But again, there is the price of the additional overhead. PDOs can be sent anytime, but they can only be used after configuration using SDOs. As stated previously, SDOs do include a significant communication overhead. PDOs include no additional protocol overhead. So let's look at a little bit into the EtherCAT slave state machine. If you're familiar with state machines, this diagram should be self-explanatory, but for those of us that are not, a state machine essentially defines which roles of operation within the drive can be passed from one to the other. As you can see, the bottom mode, the operational mode, can only be reached after initializing, putting the drive in pre-operational mode, and safe operational mode. Initialization involves using, essentially the drive is sitting there, not doing nothing, but sitting there awaiting communication. And as you can see, no user communication is allowed. In the pre-op state, SDOs are used to configure the drive, again, or configure PDOs. In safe op, SDO and PDO communication is allowed. So it's essentially real-time communication. However, the drive ignores the PDO, so it does not act on it. You can send positioning information, and the drive does not actually move the motor. So this is a good mode to use for testing, troubleshooting. And operational mode, your system is up and running, motors are servoed, and so machine is running. PDO and SDO communication are allowed. However, as previously stated, SDOs do include that additional overhead, and so are typically not used in real time. EtherCAT slave architecture. As you can see, the master initiates communication, and this is a single slave setup. Master initiates communication over EtherCAT, or over Ethernet line rather. And this is interpreted by the physical layer, Ethernet physical layer. Those of you familiar with the OSI layering network model recognize that PHY is the base physical model of a network, and that includes network interface cards, Ethernet cables, and the like. After passing through the PHY, it is then forwarded to the EtherCAT slave ASIC. And this is the ASIC, or FPGA, in the slave is really where the speed of EtherCAT comes into play. As mentioned before, as opposed to relying on software to parse and interpret data, the EtherCAT slave ASIC takes the data, the binary data, directly out of the PDO datagram and maps it into the memory object dictionary through the CPU. CPU, which is the higher level on the slave, handles currently commutation, higher level processing, digital I/O setting, profiling, torque limits, all these kind of things. But again, the secret of EtherCAT lies in the EtherCAT slave ASIC, and that is the only hardware that's specifically used for EtherCAT, and is included in any EtherCAT compatible drive. Simple PDO example. The incoming PDO position data is defined by EtherCAT standard as a 32-bit number. When that PDO comes in to the slave, it is interpreted via the FPGA again and mapped to the EtherCAT defined memory position or position memory object. So this is, in the analogy, this is the boss dropping by the cube, dropping your to-do list in the inbox. So the drive then takes this data and applies it to profiling in the current cycle. In addition, the PDO, once received by the drive, is acted upon and then returned to the drive with data profiling drives, such as the encoder's actual position, I/O status, and drive status. If there's a fault on the drive, it will be returned. An error flag will be set, and that data will be turned to the drive, which then can act upon that error status as defined in the master. PDO Exchange is shown in the diagram. This is an initial, essentially the first PDO that will be sent to the slave from the master. This is after SDOs have been set up, telling the slave FPGA where to send each byte in the EtherCAT datagram. The incoming PDO, labeled at the top of the diagram, indicates the 3 pieces of data that are necessary to activate a drive. Initially, and these go from right to left. Initially, the control word is sent. The control word is analogous to enabling or disabling the drive, so energizing the servo or turning it off. Mode of operation indicates the position, either position, velocity, or torque command, depending on whether you are in position, torque, or velocity mode. The outgoing PDO from the slave. Status word is a confirmation of the control word, telling the master that you have set me for position, velocity, or torque mode, and I am still in that mode. It's a safety precaution built in. 6062 is the position demand value, which is when the master comes up, or when the network comes up, the master essentially tells the slave, this is what I want you to define your position as. Define it as 0, define it as 100,000 counts, anything along that order. Mode of operation, again, is a confirmation of the mode of operation that you're in, as well as including amplifier state. Position actual value is the raw data from the slave, the raw encoder data from the slave, indicating the motor's current position. Digital input status, 60FD, is a bit mask number, 32-bit, that indicates the status of the digital inputs, with 1 standing in for a digital high, 0 standing in for a digital low. Real benefit of EtherCAT lies in the hardware. We have discussed this before, but it is worth accentuating. Standard Ethernet physical layer components, Cat5 cabling, network interface cards are all that are required on a PC or EtherCAT master. Uses FPGAs for fast command processing by slave units. This reduces latency to a minimum, which enables deterministic control at extremely high cycle rates, like we've discussed, up to 32 kilohertz. Physical layout of a network. The EtherCAT master is wired through each EtherCAT drive via Cat5. Hardware switches run through each drive, allowing easy daisy chaining of drive to drive. These switches are specific to EtherCAT. Ethernet switches are not compatible with EtherCAT due to the stripped-down nature. Each EtherCAT drive in this example is running a motor encoder. EtherCAT drives are also compatible or specific to either hydraulic actuators or steppers as well. However, because of the EtherCAT standard, the type of motor is transparent to the EtherCAT master. As you can see in the diagram on the right, simplified, the master sends data down from slave 1 or to slave 1, anything that is not addressed to slave 1 is immediately forwarded to slave 2, so on and so on. At the end of the transaction with slave 3 inserts its data in the return packet to the master. So now we've covered the physical layout. I'd like to talk a bit about the DMC 50,000 EtherCAT master, which has recently been released. It includes all of the features of our flagship DMC 4000 controller, the addition of EtherCAT drive support for up to 8 axes in cyclic position mode. Cyclic torque mode is supported on select drives. Contact Galil for drive-specific support. We're the only motion controller in the industry with the ability to mix and match local and EtherCAT drives. This is a crucial component of this new controller. Easily configurable and designed with compatibility and flexibility in mind. We made the command set for enabling an EtherCAT network extremely simple, allowing previous applications to easily incorporate EtherCAT drives or new applications to be built on them with very minimal application code changes. Multiple drive vendors supported at this time. I'll list those later, but we are actively looking for additional drives. And most importantly, compatible with Galil's entire line of internal servo and stepper motor amplifiers for local axes. Currently supported I/O features for each drive, in addition to position and torque mode control. Each drive supports forward and reverse limit switches on the drive, home sensor input, and hardware latch/touch probe. These allow remote sensing on the drive, allowing the master controller, in this case the 50,000, to act based on the status of that I/O. These features specifically allow access to DMC 50,000 commands and routines specific to these inputs. For example, our pound limit switch automatic subroutine. Anytime a limit switch on the drive is triggered, this automatic subroutine will fire, allowing you to include any application-specific commands you would like. For instance, shut down motors, back off the limit switch, message out to the terminal, message to the PC that a limit switch has been hit. That is important to note that this limit switch routine is not essential to limit switch function. The 50,000 is designed specifically to halt motion at a hardware level when a limit switch is hit. The limit switch routine simply provides additional flexibility. The home sensor input allows access to Galil's homing command routines, find index, find edge for finding the home sensor, and the HM command, which is those two rolled together, providing convenient homing routines. Provides access to the ARM latch and report latch. ARM latch to bring up the hardware latch, and report latch to return the position at which the hardware latch occurred. The EtherCAT error automatic subroutine, much like the limit switch subroutine, runs immediately upon a perceived EtherCAT error. So once a PDO is sent down to the drive then includes its drive status. There's a specific alarm bit that is set, and the drive interprets or recognizes this bit and immediately fires the EtherCAT error auto subroutine. This is especially convenient as specific error codes for each drive are not standardized. The EtherCAT standard has not applied to them. Drive errors include under voltage, over current, encoder errors, a whole slew of potential codes. The EtherCAT error automatic subroutine allows for easy parsing and identification of the drive in order to handle those specific error codes. These are examples of setting up a simple move, a position relative move, on a local axis, where you can see the motor is energized with the servo here. Command a position move, begin motion, and then after motion, set bit 1 as an indicator to the operator that the move is complete, and then also message out to the PC that it's complete. Now you can see on the bottom right that this code is almost identical with the addition of only 3 commands. MT10 tells the controller that the A axis is now configured for EtherCAT position mode. EX-1 is EtherCAT Exchange -1. Assign the first EtherCAT drive on the line. So the first one physically down the line from the master is now assigned to the A axis. EU1 brings up the EtherCAT network, and now you're ready to go. And as you can see, the code below is identical. So this is really what provides a huge amount of flexibility in the DMC 50,000 in either editing previous existing application code or implementing new applications. DMC 50,000 hardware layout. This is kind of the end-all, be-all. You can see the 50,000. The bottom 3 drives are EtherCAT drives on servo motors. Again, these servo motors, these can be servos, steppers, hydraulic actuators, linear motors, depending on what the EtherCAT drive is configured to run. The red lines to servo motors indicate motor or power lines from internal 50,000 amplifiers. The green lines indicate step and direction signals running to individual stepper drivers, which then run stepper motors. So it really is flexible and configurable for whatever your application requires. And again, this is a function that is unique to the Galil DMC 50,000. So a list of compatible Ethernet drives, which are at this point are all rotary servo motors, motor drives with incremental encoders. And as mentioned, we are actively looking to include support for additional vendors. We're seeking input from customers. We're really letting this is our standard line, but we are looking for customer input, waiting for the market to guide where our next drives to be supported. Our R&D drive support process has become pretty streamlined. In summary, EtherCAT protocol is gaining traction, robust and efficient solutions demanding large-scale automation applications. EtherCAT is specifically designed for, as mentioned, large-scale applications. For small local applications where the controller is in close proximity to the drive, EtherCAT may not be able to reap the benefits of EtherCAT. Built on the physical and data link layers of Ethernet communication, making the technology more accessible right off the bat. The network engineers is familiar with the physical and data layers being network interface cards and Cat5 cable. There is a higher controller and drive cost associated with EtherCAT controls. However, this is easily offset by the use of pre-existing, easily attainable hardware. This also reduces maintenance and installation costs. Running encoder lines and motor command lines to individual drives over 20 meters is a lot more expensive to install and maintain. If in the event of a line being cut, some kind of error in the system, it's much easier to replace a Cat5 cable as opposed to troubleshooting and rewiring 8, 9, 10, 12 different lines. And due to the EtherCAT communication protocol, networks are easily expandable, as we've seen, modifiable, and simple to maintain. Since the EtherCAT standard specifies where those memory locations we're writing to are, it's simple to change out drives, which are transparent to the master. So at this point, I'd like to open it up to questions. Our VP of Engineering, Coach Shaw, will join us to cover any questions you may have about this presentation.
All right, thank you, Matt, for that information. And we're going to take questions from the audience now. So if you have any questions, you can put it in the panel box on the GoToWebinar. Okay. Our first question that we have is, I am already using a Galil Ethernet TCP IP-based controller for my 6-axis application. Should I consider moving to the EtherCAT-based controller?
As we previously discussed, whether to move to EtherCAT or not is primarily a question of what the application requires. In situations where the amplifiers and motors are close to the controller, leading to a small footprint, EtherCAT is really not the best fit. It's essentially the best fit is in large industrial applications long-distance wiring, noise immunity. Again, instead of wiring encoders, motor command lines, it's much easier to plug in a Cat5 cable. Cost increase from EtherCAT drives will be justified, though, with saving material, cables, maintenance associated with a centralized solution. Next question.
Okay, our next question is, my application uses a combination of electrical and hydraulic servos, as well as 2 low-power stepper axes. How is this addressed by EtherCAT connectivity?
Again, since the EtherCAT standard essentially defines where that profile data is written to, type of motor actuator is transparent to the master. You tell either the servo to move position, stepper to move to a position, actuator to move to a position. Specifically, the DMC 50000 adds to the flexibility by offering simultaneous control of EtherCAT axes as well as local axes, whether they be stepper or servo, and those can include our low-cost internal amplifiers, saving costs and maintenance.
All right, our next question is EtherCAT a deterministic or a non-deterministic network, and which is better?
Similar to the question about whether Ethernet or EtherCAT is better, it isn't a question of better so much as a question of appropriate to the application. Deterministic versus non-deterministic. EtherCAT was designed specifically for closing the servo loop over the wire. Essentially, as we've seen, closing the servo loop over long distances through efficient communication, so stripping down the Ethernet packet, as well as fast processing by EtherCAT-specific ICs. Type of tightly coupled control demands a deterministic network, using a single motion controller to coordinate communications between all slaves on an EtherCAT network while acting as a gateway to a host PC guarantees deterministic performance, as opposed to running a master as a PC where you're dependent on software operating systems. It's best to use a dedicated controller. Okay, do we have any further questions?
Yes, our next question is, how is local and remote I/O sampled in an EtherCAT distributed control system?
Okay. In the same way that position data is passed between the master and the slave over PDOs, again, allowing, or due to that great EtherCAT standard, the I/O status is also stored in specific memory addresses, which then can be written to the PDO returning from the slave to the master. With the DMC 50000, the controller can provide options to both EtherCAT I/O as well as Galil's Pocket PLC, the Rio 47000, which also uses Ethernet TCP/IP communication.
All right, we have one last question.
Okay.
Are advanced modes of motion, such as helical interpolation, linear and circular interpolation, or contouring mode, supported in your EtherCAT master?
Okay. Yeah, the short answer is absolutely. One of the driving forces behind the design of the 50000 was to allow access to our entire set of advanced modes of motion. Basically, if you can do it on a local axis on the controller, you can do it on an EtherCAT axis. So in addition to simple point-to-point motion, 50000 is capable of helical, linear, circular interpolation modes, contour, PVT modes, as well as electronic cam and gearing modes. Additionally, and this is what we consider to be one of the major strengths of our controller, these moves can be coordinated between local axes and EtherCAT axes simultaneously. Essentially, the EtherCAT drive becomes transparent to the master. As far as it's concerned, it's a local axis, which again adds a huge amount of flexibility.
All right. Thank you, Matt, for sharing that insightful information with us. Thank you also to everyone who attended the webinar today. Finally, thank you again to our sponsors, Galil Motion Control and Electromate. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. All questions submitted through the webinar screen will be answered by email after the conclusion of today's webinar. Be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Thank you, and have a great day.